We're talking about the detachment fault and the metamorphic core complex at the distal continental margin of the South China Sea. This work is done together with Jianye, Patrice, and King MacLeay. I first talk briefly about the South China Sea tectonics, and this is followed by metamorphic core complex at the northern South China Sea passive margin from 2D and 3D seismic studies. Later, I will show the analogs from the Mid-Atlantic Ridge and North American Cordillera, Mediterranean Aegean area. Finally, I conclude with a wide continental rifting model of the South China Sea. In the latest Cretaceous, a large ocean here named as Proto-South China Sea was situated between Borneo and South China. So this Proto-South China Sea in the Paleogene subduct northwards, resulting in a wide occurrence of the back-arc rift basins, which finally lead to the formation of the current South China Sea. In the Paleocene, the Proto-South China Sea also subduct southward and finally disappeared, with the only occurrence of the current South China Sea in place. So the current South China Sea has a very wide continental margins, up to 1,000 kilometers in the north and more than 500 kilometers in the south. So it has extended a vast area. Recent IODP campaign has not discovered large exposure of continental mantle, like what we have seen in the North Atlantic margins. But the availability of the industrial seismic datasets has made us be able to image continental crust structures. To be notably, the South China Sea has a very high heat flow, up to 110 milliwatts per square meter. Our study area is the distal part of the South China Sea northern margin. This is covered by 2D and 3D seismic datasets and is constrained by IODP wells. So from the deep seismic section, we see the borehole very clearly. And we also see the dome structures. On top of that is a ridge that bounded to the south by a low-angle detachment fault. Zooming into this area and pass through the seismic, we can see the adulation of the borehole at the bottom. And here we can see the dome structures and the ridge on top, which is bounded by a very shallow low-angle normal fault immediately north. Then, after the disappearance of the detachment faults, come up with the oceanic crust. So we interpret this seismic section and show the crust structure of the passive margin, and with a particular stress on the appearance of large detachment faults. So we use 3D seismic data to imaging the geometry, the detailed geometry of the detachment fault. It shows the grooves and corrugations on the detachment faults and the supra-detachment fault as well. Using the azimuth attributes, we can see the grooves and corrugations again and more clearer. The intrusive boundaries can also be outlined by the distortion on the detachment faults, which showing that the intrusives come below the detachment faults. So this observation of the grooves, corrugations are very much similar to the oceanic core complex that has been exposed at the sea bottom, at the sea flow of the Mid-Atlantic Ridge. So we come up with the conclusion that the detachment fault we see actually exposed a large area of metamorphic core complex. In the western part of the 3D seismic, in the eastern part of the 3D seismic, we see a large shallow angle high reflectors, which is a detachment fault. On top of that is a supra-detachment basin with seawater dipping secondary structures. Below the detachment fault is the seawater tilted nappe. It has a homogeneous reflector, and this is wrapped by high amplitude reflectors that has shown the nappe fold or isoclinal fold structural geometry. In the western part of the 3D seismic, we can see the high reflector is actually a detachment fault. This fault has been folded and faulted strongly. In the middle part of the section, the detachment fault has been domed upwards together with the supra-detachment basin. The strata with the basin and the faults with the basin are also deformed together with the detachment fault. Below the detachment fault is homogeneous reflector, and that's showing the finger-shaped geometry, which we think is a magma. And below the magma is a high amplitude chevron geometry that of the reflectors. From the attributes, we see that the isoclinal fold is clearly highlighted. Based on the observation, we compare it with a basin and range province that also is a back arc extension basin, and has been studied very well for the co-complexes. In this area, the co-complex model showing the corrugation of the detachment fault, supra-detachment faults, and the distributed simple shear and magmatic deformation below the large-scale detachment fault. From a cross-section point of view, the foot wall of the detachment fault will tilt it backward, just like what we have just seen in the Lee detachment fault. And the large detachment fault has large distance displacement and has broke the brittle part of the upper crust and exhumed the lower continental crust with simultaneous intrusion of the protonic intrusives. Another very famous area that's showing the metamorphic co-complex is Aegean area. This area is also back arc basin. It has a high heat flow up to 120 milliwatts per square meter. The Aegean co-complex show characteristic extensional perpendicular dome, extensional parallel domes, and below the detachment fault is the crustal-scale nappe fold. From the cross-section, we can see the footwall will tilted backwards, and large detachment faults expose the lower continental crust material with the intrusion of the syntectonic protons. So based on the observation and the comparison with the oceanic co-complex and the metamorphic co-complex at the Basin and Range provinces and the Aegean area, we come up with the metamorphic co-complex model of the South China Sea Pacific margin. It shows the corrugations, the loops on the detachment fault, and the intrusives that in some places form the dome structures, and the nappe folds below the detachment fault. The nappe folds, the stratification is mainly made up by the mannanite layers. So the structural models of the distal part of the South China Sea is mainly composed of by the large detachment faults. This detachment fault has thinned the continental crust by breakup of the brittle part of the upper continental crust and exhumed the lower continental the continental crust. This occurred with simultaneous intrusion of the protonic rocks. And the thinning process will immediately followed by the break up of the continental crust and the formation of oceanic crust. So that's what we have just seen and concluded in this presentation. Thank you for listening. Thank you.